Hello everyone, my name is Jonathan. Welcome to Exoplanets project. We have three group members, me, Brian, and Karthik. Without further ado, let's dive down into the knowledge base. So there are five common types of exoplanets. Terrestrial, which are Earth-like planets made of rocks, but not very common in our discovery. The second is the gas giants, like Jupiter's or Saturn's. They are mostly made of gas with a tiny solid core. And super Earth. There's no examples of super Earth in the solar system, but there turns out to be a lot of super Earths from the exoplanet dataset. Also, the mini Neptunes. They are made of ice and rock, covered with a thick atmosphere. Also, hot Jupiters, which are Jupiters close to the host stars. That's why they are hot. And there are a few common discovery methods. Microlensing, which is based on general relativity. When a planet passes between Earth and the host star, its gravitational field will bend the starlight. And based on how much starlight is curved, we can infer on the planet's mass. Microlensing has a bias on heavy planets, and so does the radial velocity method, because when the planet and host star actually forms a binary star system, when the star moves closer to the Earth, it will compress the wavelength, which means wavelength gets shorter and blue shift. On the other hand, when the star moves away from the Earth, wavelength got stretched and redshift. So based on how much the spectrum of the based on the spectrum of the host star, we can determine the existence of exoplanets. Also has a bias on massive planets that are close to host stars. Also has a bias on the plane orientation, orbital plane orientation. Direct imaging is the most direct method, but unfortunately is least common, simply because planets don't like their host stars radiating light. They only reflect the light from the host stars. And it's the transient methods which become increasingly popular in recent years with the advancement of Kepler telescope. So above all discovery methods have a bias on heavy planets. That's why most of the planets we have discovered so far, which we will see later, are heavier than Earth, much heavier actually. And radial velocity method and transient methods are the most dominant methods in this field. And they are complement to each other. From the NASA's database, it contains over 5,000 rows and 92 columns, but most of the columns are not useful. For example, the discovery facility, solution type, and controversial flag. So we removed some unuseful columns and analyzed the missing values. And turns out there's a lot of missing values in some columns, like the planetary insolution, which means how much radiation it receives from the sun, and the stellar spectral type, planetary equilibrium temperature. But later you will see in our data analysis, those columns are turns out not very important variables. So it is okay that we don't have all of the values. And also we impute the missing values based on the known values of all columns based on the KNN imputer, which uses the closest field number of neighbors to infer the missing values. And the next part is about some insight about the dataset. First is the distribution of number of stars in the system. Turns out unary star system is majority, which is no surprise. And the distribution of number of planets in the stellar system. The caveat for this is we haven't discovered all of the planets in the solar system yet. So this histogram is actually biased towards the left. As an anecdote, we may not even discover all of the planets in our solar system yet, let alone the exoplanet system, right? Distribution. So I break this histogram into 4 parts by the number of stars. Turns out, if the system has more than 1 stars, the probability of discovering planets becomes lower. That makes sense because it's an unstable system. So planets may be thrown away or eaten by the host stars. Things might be better for the binary system because binary is stable, but for the ternary and 4-star system, planets are very easy to be thrown away. Here's some variable dependency analysis. For example, here we test the bias of discovery methods. So radial velocity has a bias on the long period and the massive planets, but the transient method has a bias on the short period and massive planets. So nearly all methods have a bias on the massive planets. So that's why you can see on this scatter plot, most of the planets we discovered have planet mass above our Earth mass. So the green line is the Earth mass, and the period is also biased towards shorter than the Earth period. The blue line indicates the Earth year. So most stars have less than 1 year to rotate around the star. So this from this graph, it gives us an inspiration or the theme of our project, which is to classify different types of the planets based on different features. Like here, we only use two features, planet mass and orbital period. And our hope is to, by using more features, better selecting the important features, we can classify those planet types more accurately. As you can see in this plot, the gas giants can probably be divided into two categories. First is the short period, the other has a long period. The short period is closer to the stars, to the host star, and does have a high temperature, and in astronomy it's called hot Jupiter. And the long period Jupiters are the normal Jupiter as we see in our solar system.
All right, this is the habitability portion of the exoplanets research, and I determined that the best way to eliminate the most amount of planets is to first detect the terrestrial planets. So that's what I focused on, so that I can look more in depth at machine learning techniques rather than synthetic variables. I then carry on to pre-process the features, and I just use the standard scaler, and I move on. So I'm using XGBoost, which is a tree ensembling method that is successive. So instead of bagging where you're averaging a bunch of different tree models, you're actually training the next tree model to improve upon the last tree model. So XGBoost has been pretty popular lately, and that's why I chose to work with it in this assignment. So initial training is really good. Training accuracy is 100%, and test accuracy is almost 97. I think it's worth noting that this is a multi-class classification problem, so it is a little different than regression, which I also tested out in the process of this project. So being that it's multi-class, I wanted to look at the accuracy by each class, and I can see that gas giants is the most accurate, with terrestrial being one of the least accurate. One thing worth noting is that there is an unknown category, and this may limit the results of our machine learning techniques. I also quickly review the different aspects of a classification report. So the goal here is to explore the XGBoost model and improve it as much as we can, and explore the different hyperparameters available for tuning. So first I explore just k-fold cross-validation, and I try to get the cross-validation mean accuracy near the test accuracy so that we can represent it better in further tuning. So in this, I'm leaving out half of the data for test, and I'm using half of it for training, and we can see that they are pretty close. So although our accuracy is pretty high, we still have some more questions. What hyperparameters can we tune, and what are their importances? So moving on to hyperparameter tuning, we are first going to look at the importance of each parameter separately. And I researched these before writing this code, and I hoped to validate what I researched by plotting the different accuracies, the cross-validation accuracies, while I change the parameters. So I start out with this grid, and for each of the 9 different hyperparameters, we'll go through one by one. We have max depth first, which is the max number, or the max depth of the trees. And from this, it's determined that 5 gives the best, which is a slight improvement over the default of 3. The learning rate is next, and it also seems to have an impact on the accuracy, not very much as we can see by the range of the y-axis. The number of estimators is also important. It's the number of trees that we're stacking. The min child weight is the improvement that we need to get in order to continue growing the tree, and we see more of a cyclical response here, and so the results are not as clear as the previous ones, but the next two are going to add some randomness into the model, and the trends are pretty clear for subsample and for column space. Subsample is how many we're using, how many samples we're using, and the column space is how many features we're using. So the more features we use, from 0% to 100%, the slightly more accurate you're going to get, but the higher risk of overfitting. Gamma can also control overfitting, and so it's got the same kind of trend. Next, we're going to look at L1 and L2 regularization for feature selection, and it seems like no feature selection is best here, and that very little ridge regression is good. These are very tight ranges, and so this suggests that regularization is not very important. So now we're going to conglomerate all the parameters that we just tuned and see if it results in a better model, and disappointingly it does not. So we go back and we relook at the accuracy for just one of the tuned parameters, gamma, and we find that this is an improvement over the initial model, although not by very much. In terms of absolute value, it is a good improvement overall because we are at such a high accuracy. It becomes exponentially harder to increase accuracy the further we get towards 100%. So these results suggest that we should tune hyperparameters simultaneously rather than one at a time. And so the next thing I dive into is random search cross-validation, where we start with a bunch of parameter grids, the same one as last time, and we go through a set number of iterations. And one thing I wanted to look at here, because I thought we might not see continual improvement, was the effective number of iterations in random search cross-validation. And so I create this function definition and I call it in a for loop while changing the number of iterations we go through. And unfortunately, I did run this up until 100 candidates or 100 iterations overnight, but the results were accidentally wiped. Luckily, they didn't change very much, so we have this slightly shorter graph showing the impact of both iterations and runtime, which I kept track of. So we can see that these two graphs are very proportional, and that the more iterations we do, we get a logarithmically decreasing increase in performance. So after just about 25 iterations, we've hit the maximum accuracy that we can. And we also see, interestingly, that training and test accuracy both get bumped up at the same time. So we're going to take a look at the best model we found through random search, and unfortunately it did not find as good of a model as just tuning gamma only. This could be because of an unlucky seed or something else, but it wasn't very good. We can see a slight decrease in precision across all classes. So overall, this section of the report demonstrated XGBoost and the different importance of the hyperparameters. I think it's really interesting how many there are. There are 9 that we looked at in this section of the report. Also interestingly, feature selection was not found to be very useful, and I determined that you should tune hyperparameters simultaneously, although in this report we didn't see much of an improvement there. So I think tuning individual parameters first is a good way to start, and that we should try this on different data sets to explore XGBoost's capabilities further. In future work, it would be interesting to use Bayes search cross-validation. However, I could not get this working by the due dates of the project. There were some heavy modifications that needed to be made in terms of how the parameter distributions were sent into the model. There was lesser ability to handle integers versus floats in this setup in scikit-learn. So that's one barrier to implement this in the future, but if there were more time in this project, that's one thing I'd work on.